Good morning again. This is your friendly heavy physics teacher, and I'm here with a lesson for my Regents Physics class, which went double for a lesson for my college physics class. For the Regents Physics class, this is for U11 lesson 5, and we're going to be talking about the Doppler effect today. Okay. Um, the Doppler effect I'm including with sound because for us, for human beings, it's most evident with sound waves. Okay. But the Doppler effect applies to all kinds of waves, regardless of what kind of wave it is. The Doppler effect was originally proposed by a scientist by the name of Christian Doppler back in the 1800s as an explanation for a weird phenomenon that astronomers were noticing in relation to the light that they were analyzing coming from stars. In particular, there was a binary star system that had some very curious properties to it. At one time of the year, when they observed the star and they analyzed the spectrum of the two stars as they were moving around each other, um, when they looked at that spectrum of the star as it was moving away from the Earth relative to the Earth's own motion around its own star, they would notice that the spectrum of it had numbers that said that the hydrogen spectrum, the line spectrum, if you remember from your chemistry class, the line spectrum, all of those numbers were actually shifted down toward the red end of the spectrum. And when they looked at the light appeared to be shifted toward the red end of the spectrum. And the whole shift, everything. So there's four spectral lines to hydrogen: a red line, a green line, a blue line, and a violet line. And all of those had been shifted down. The red line was more toward the infrared. The green line was more yellowish than it was green. The blue line was less blue. It was more toward the cyan part of the spectrum. And the violet line was more toward the blue part. Okay. So everything was shifted over toward the red end of the spectrum. All right. But later in the year, at a different time of the year, when the star orbiting its binary neighbor was now moving around and coming toward the Earth, they noticed that that whole spectrum was shifted away and up beyond what the normal spectrum from hydrogen should be. And it was shifted toward the blue end. So the red appeared more orangey, the green appeared more cyan, the blue appeared bluer or more toward the violet, and the violet was moved almost up into the infrared due to the motion. Well, at the time they couldn't explain it. Christian Doppler proposed that it was the physical motion of the star in its orbit. When it was moving away, it forced the waves of light to lengthen their wavelength compared to what we would normally measure for something sitting still. All right, and so they began doing a lot more analyses of light, and then the scientist Brice Ballot, a French scientist, did an experiment with trumpeters on a moving train. And what he did was very interesting. He had one set of trumpeters. They all tuned their instruments to the same tuning note. Okay. And he had one set of trumpeters stand on the side of a railroad tracks, and he used a very long straight path of railway in France to do this experiment. He had the engine with a flat car back way up and then get up to speed. And at a certain moment, there were flags set up so that they could all see and start playing at the same time. And when they passed these flags, a group of trumpeters on board the train, on board the flat car, would all play this note that they all, predetermined would be played. And the trumpeters on the side, on the ground next to the railroad track, also played the same note. And so Bice below rode the train. And so he was traveling along and he's sitting there, and the trumpeters begin to play on board the train. And he hears the note the way he would normally hear it, as if he were at rest. And yet he's moving with the trumpeters. And so as he moves toward the trumpeters that are on the side who aren't moving, he notices that he hears their pitch as higher than the pitch he hears his trumpeters on the flat car making. So the train stops. He gets off and stands with the trumpeters on the side of the railroad track. The train backs up, vroom, comes roaring back again, and the trumpeters on board the train, they're playing their note. The trumpeters on the ground on the side of the railroad track are playing their note, but Bice below notices that the trumpeters on the side of the railroad track are playing the tuning note he expects, but the ones moving toward him are the note appears or sounds higher. The pitch is higher to him. Okay, and this confirmed that it was the motion of a wave source, because it was sound, not just light. The motion of a wave source affects the frequency and wavelength that wave has to an observer, based upon the relative motion of the observer and the wave source. And we have now come to call this effect the Doppler effect. Okay, the Doppler effect definition. All right. Doppler effect is the apparent shift in frequency and wavelength of a wave due to the relative motion between the source of the wave and the observer who can experience the wave. All right. Now, anybody who's a NASCAR fan has experienced the Doppler effect. All right. The cars coming towards you on the racetrack, they have a higher pitch engine sound than as they go by. All right. And there's that characteristic sound. Okay. The pitch is higher as it comes towards you. It's lower as it moves away. We're not talking about loudness here. Loudness, yeah, a faraway object is going to sound softer, and as it gets towards you, the sound loudness is going to get louder. Same thing with light, all right? If a light source is far away, it doesn't appear bright. That's not the light's frequency. The color of light is its frequency. The pitch of the sound is its frequency, okay? And the same thing can be observed on water. The same thing can be observed with any kind of wave. If there is relative motion between the wave source and the observer. So it could be the wave source that's moving, race cars. It could be the observer that's moving, okay? You're driving in a car toward a fire station, and the fire station is sounding its siren. Well, you'll hear the pitch of the siren higher than someone standing next to that siren at the fire station, okay? Okay, the way I like to think about the change in frequency and wavelength that happens with the Doppler effect is the relative distance between the source and the observer getting smaller, or is it getting bigger? And based upon that change in distance, that's going to determine our motion. So we will notice a frequency increase. We will notice a frequency increase if the distance between the wave source and the observer is decreasing. Doesn't matter which one's moving, okay? If the wave source is moving toward the observer, we're going to hear a frequency, a pitch increase. If it's sound, we're going to see a frequency increase, a shift toward the blue frequencies of light. if the wave source is moving toward us. If we, the observer, the person making the observation about the sound or light or water wave, if we are moving toward the wave source, we will notice a frequency increase. Okay? Right? And so that's what we're looking at here. So, as a wave source moves toward an observer, or an observer moves toward the wave source, or both are going on at the same time, both are moving, then the frequency must increase. The amount of increase depends on how quickly that motion is happening. Conversely, if the distance between the wave source and the observer is increasing, they're getting farther apart, then that means that the frequency must decrease, or the wavelength is lengthening. Okay, so as a wave source moves away from the observer, or the observer moves away from the wave source, you're going to get a lower frequency. Okay, now all of this is happening because the medium hasn't changed. All right, if we're talking about sound, we're talking about air normally. All right, and for a given temperature range, all right, the speed of sound in air will be one number. Doesn't matter that the wave source is moving. Doesn't matter that the police car is coming towards you or moving away from you. The speed of sound is the same. But physically, what's going on is, as the police car is coming towards you, sounding its siren, it's making the sound and moving with the sound wave that's trying to get away from it in front of it. So that physically shortens the wavelength. Please download the notes and look at them. I've physically drawn how this looks. So check that out, please. Download the notes. Check out what's going on with the waves physically. Okay? So you've got the police car sounding its siren, going, trying to move this way. Well, the waves that it's making are traveling away from it in front of it. They're also traveling away from it behind it. But because the police car is moving this way, it's moving with the waves that are going. So think about it this way. This hand is my wave front from the siren. All right. It's going to separate. It's going to get a little bit farther in front of the car. But think about it behind it. It's actually going to be moving away faster. In that way, physically in front of the siren, or in front of the siren, in front of the police car, the waves that it's making, the sound pressure waves that it's making, are getting scrunched together. So we've got shorter wavelength between the high pressure zones. Okay. Well, if the wave is shorter, that means the frequency is higher. In other words, an observer is going to be encountering more waves per second moving by it for that speed than normal. Okay? Police car sitting in a stop sign, sounding its siren, waiting to go across when it's safe. Okay? Because people are oblivious to police officers. Oh, I can't believe some of the drivers around here. Sorry, totally distracting myself with that. Folks, turn your radios down in your car. Heck, turn them off. It's a distraction. And listen for emergency vehicles. Listen, watch, see. All right? Don't make them wait at a stop sign because they're afraid that you're not paying attention coming down through when you don't have the stop sign. All right? It's polite to give way. Police officer sitting in a stop sign, sitting in a stoplight, waiting for it to be safe. The siren is going to make a particular noise. When he's moving, when she's moving, the siren that she is using is going to, in front of it, the waves squish together. They're going to spread out behind it. The speed of the wave is the same regardless of whether the police car is moving or not. Same thing for light, okay? If we are looking at a star far away from us and it's moving toward us, we are going to notice that the light coming from it is going to be squeezed together. The wavelengths are going to be squeezed together. The frequency is going to be higher because we're encountering more waves per second than normal. This is the essence of the Doppler effect, okay? So, what does this mean as a rule of thumb for the different kinds of waves? Okay, for sound waves, if the motion is toward the source, in other words, the distance between the source and observer is decreasing, then that means the pitch is going to increase. You'll hear a higher pitch, higher frequency than you normally would. That's the way we normally experience sound. If the motion is away, the source is moving away from you, the fire truck is pulling away from you, you are moving away from the fire station, you are moving away from a train sitting in the train station sounding its horn, okay? The motion is away, you're going to hear a lower pitch, all right? For light, all right? If the motion is toward, if a star is moving toward us, okay, we have to talk about it in those terms because the speed of light is so high, you have to have relatively high velocities to really notice any shift in the frequency of light. So if the motion is toward us, if the distance between the light source and the observer is decreasing, then you'll see a blue tinge to all of the light. Red becomes yellow, yellow becomes green, green becomes blue, blue becomes violet, violet becomes ultraviolet. All right, that's what's going on with light. Okay, for motion away, we have the red shift. In other words, all the light, instead of being its normal color, it would be shifted down toward the red end of the spectrum. So violet would become blue, blue would become green, green would become yellow, yellow would become orange, orange would become red, red would get pushed down into the infrared end of the spectrum. Okay? So for water, all right, any of you who own a boat or go to a lake and can observe the motion of a boat on a relatively still lake, you'll notice that at relatively low speeds for the boat, when the boat is moving forward, the waves made by the boat have a shorter wavelength in front of the boat. The boat is not planing. The boat is not, going faster than the wave it's making. Okay? The boat is going relatively slow compared to the speed of the wave in the water. So when that happens, the boat's motion is forcing the wavelength to shorten in front and get longer behind. Okay? Now, for those of you who own a boat, you often go faster in the boat than the water can move on its own with the wave. And you get that characteristic V-shaped wake flowing out behind the boat. That's called a wave boom. And that's because you, the source of the wave, the boat moving through the water, are actually moving faster than the wave motion itself in the water. For sound, we call that a sonic boom. Okay? If a sound source moves faster than the speed of sound it is making, all right? In other words, an airplane flying faster than 343 meters per second, room temperature airspeed, okay? It will create a sonic boom. Now, again, make sure you look at the notes, download the notes. The last page of the notes is where I talk about sonic boom or wave boom created when the source of the wave is moving faster than the wave can move through the medium. okay? This creates a shock wave. That shock wave is a constructive interference of the overlapped waves. Now, for a boat, that's what creates the V you see in the water. In air, you don't really see the sonic wave except for those really special photographs that they've made of planes as they're breaking the sound barrier. It creates a condensation cone around the plane, okay? Um, because of the extreme low pressure created by that constructive interference in the air, okay? Now, for light, there are times where charged particles can move faster than the speed of light in water. Not the speed of light in a vacuum, speed of light in water, which is 33% slower than the speed of light in a vacuum. All right. And so if you have a beta particle zipping through water at, say, 280 million meters per second, it's going to create a shock wave moving through that water that is going to excite the water molecules and cause them to glow with this particular blue colored light. Okay, look up Cherenkov radiation and you'll see pictures of it from nuclear reactors and nuclear reactions. Okay, this is a light boom. All right, where if you're going faster than the speed of sound, you call it sonic boom. Cherenkov radiation is a form of light boom. All right, and that's happening because charged particles are creating an electromagnetic disturbance due to their motion through the water at faster than the speed of light. Okay, the shock wave created from that motion is the shock wave that excites the water and causes the water to glow with that blue glow. Okay, so there you have it. The Doppler effect happens with all waves, not just light, not just sound. Okay, a boat moving through the water is creating a Doppler effect. A police car moving down the road sounding its siren is creating a Doppler effect. The motion of the Earth going around in the solar system is creating a Doppler effect when we look at other stars. Okay? Interestingly enough, the rotation of the sun, as the side of the sun that's moving toward us is giving off light, we will notice that the sun from the light from that part of the sun will be slightly blue shifted. As the sun rotates around and then that side of the sun moves away from us, the light coming from that side of the sun is red shifted. We've measured it. Okay? The Doppler effect happens with any kind of waves. Thank you for watching. This has been your friendly heavy physics teacher one more time. And hopefully one of these days we'll see you back in school. Have a great one, and signing off.